Good evening and welcome to the Scientific Adventures of Beardman. Today we're going to be taking a look at the Doppler Effect. Okay? The Doppler Effect is a change in frequency of a wave caused by the motion of the source, the motion of the observer, or both. Okay, now the source is of course the source of the sound, and the observer is the observer of the sound. Well, let me be more vague, even though we're going to talk mostly in terms of sound. The source is the source of the wave, and the observer is the person observing the wave. So that could be sound, it could be some other kind of mechanical wave, like coming off of the bow of a ship or something, or it could be electromagnetic wave. It could be light. So first let's take a look at the idea. Well, first of all, when a sound happens, it happens at a point, okay? Let's just say something's sitting there playing the trumpet, okay? It's making a noise. The trumpet, the vibrations of the lips of the person making the sound are vibrating. As those compress, that sends out a compression. Now, that compression heads out in every direction, like ripples in a pond. And so our first crest is here. Now, let's just say we're listening to a 10 hertz sound. Okay, that's, I think, below our ability to hear, but let's just pretend for a moment. So if it's 10 hertz, that means one compression is sent out every 10th of a second. The period is 1/10, the inverse of the frequency. And so 1/10 of a second later, this crest you see here will be this far away from the center, which is where the sound was made. Now, after 2/10 of a second, the first one will have traveled a little bit further, and the second one will now be that far away. And after 3/10 of a second, the first one will have traveled even further. As you can see, as we keep progressing here, 4/10 of a second, 5/10 of a second, and finally 6/10 of a second. We can see here this is what will happen. Now, if you were standing in any one of the places around this circle, these waves would get to you one every 10th of a second. Okay, and that's what we are kind of used to talking about in terms of sound, or in terms of waves reaching your ear. We talked about that in the last video. First, let's talk about what happens if the observer is moving. So we see here we've got our concentric circles of our waves. They were released one every 10th of a second. Okay, well, if your observer is standing here by this outer circle, the first crest, the first compression that was released, if they stay right there, this next compression will reach them 1/10 of a second later. So they hear a frequency of 10 hertz. Okay? But if they were to move towards it, then as they move towards it, it's still moving out, and that sound we know will get out here to where the first crest is in 1/10 of a second, which means if the observer is a little bit closer to the sound, well, then that means they will have passed that sound in less than 1/10 of a second. And therefore they're going to hear a frequency greater than 10 hertz. Okay? Or the opposite could be true. You could take it to an extreme. Let's say this person is moving away at the same speed as the sound is traveling, at the speed of sound, then that sound will never catch up to them. They certainly won't hear 10 hertz, but if it's something less than that, the sounds will catch up to them, but at a much slower rate. And so they'll hear something at a much lower frequency than the 10 hertz that was produced. Okay? Now let's see what happens if the source is moving. Okay, so if the source is moving, let's go back to our circles. Our first sound wave leaves, but as that happens, as that wave has traveled that far, the source has now moved. Okay, and as it moved, we now get a concentric circle around where it now is. And so after that first one is moved, the first one's still moving out around the place where it started, but the second one started in a different place. So we see something like this, where we see a shift in that second compression as it travels out. And if this continues to move as the sound waves go out, we'll see a pattern that looks something like this over the course of 6/10 of a second. Well, you can see that if you're standing over here on the side where they're all clumped together, you're going to hear the waves more frequently, at a greater frequency than 10 hertz, because each one was released from a little closer to the observer, because the source was moving. So each one had a little bit less distance to travel, and so they clumped up, and he'll hear, and the observer at that point will hear them at a higher frequency. Okay. Whereas if you're standing on the other side, if the source is moving away from you, you can see these wavelengths have spread out. Each one was released from a little farther away, so even though they were released one every tenth of a second, they're going to get to an observer, a stationary observer, at a speed or a time greater than a tenth of a second, because each one was released from a little farther away. Okay, we can see that in this animation here as the little dot is moving to the left. We can see that that's stretching out the wavelengths that are heading to the right, and then as it goes back the other way, we see them being compressed together. Okay, we could have drawn the animation on the other side and it would have been compressed first and then spread out. Okay, sorry, compact would be a better word, because compression is each wavelength, okay, if we're talking about sound. So now we have names for these two phenomena. First, there's something called the blue shift, and that is if the source and the observer are moving toward each other, the frequency observed is higher than the frequency produced. Okay, as we saw from both of the examples before, if you're moving into a stationary set of waves, you're going to cross them faster, and so the frequency will be higher. Or if it's coming to you, it's going to bunch them up, and so you'll hear a higher frequency. Either way, if the relative motion of the two objects is getting closer together, you'll have that increased frequency. Now keep in mind, with sound, that means a higher pitch. And if you're in the light spectrum, if you're talking about light waves moving, that would create the light being shifted toward the blue end of the spectrum. Really, it'd probably be better to say towards the gamma ray portion of the spectrum, but we tend to think in terms of what we can see, which is the visible range, and that would be towards the blue end of the spectrum. So we call it a blue shift. Okay, that's why it's called blue shift, because everything's shifted towards the blue end of the spectrum, at least visible light is. Okay, everything's shifted towards a higher frequency. The other type is called red shift, and that is if the source and observer are moving away from each other, then the frequency observed is lower than the frequency produced. Okay, once again, if you're in a stationary set of waves but you're moving away, each one's going to have trouble catching up to you, or it's hard to catch up, and so it's going to take longer, and so you'll have a lower frequency. Fewer will go past you each second. And also, if you're on the side where the waves have stretched out, then you'll hear the lower pitch. Lower frequency, which if you're dealing with sound is a lower pitch way down here. And if it's light, then that's going to be shifted towards the red end of the spectrum, or really probably towards radio waves. But once again, if we deal with the visible part, that side of the spectrum is the red side. Okay, so that's called a red shift. So one place we see this fairly commonly with sound is with race cars, or cars in general, because a car goes fast enough that it bunches up or spreads out the wavelengths. So as we hear a car coming towards us, we hear as it passes us, because when it's coming towards us, that wavelength was increased, we heard a higher pitch. So while the engine to the person in the car was going, the person listening to it come towards them heard, and then as they were right next to the car going past them, they heard the actual same sound, same frequency that the car was, because it wasn't going towards them or away from them, and then a moment later it was going away from them, so they hear a pitch lower. Once again, that sounded something like, or if you want to think of it in terms of a siren, it would go, woo, 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 woo. Because its increase is coming towards you and decreased frequency as it's leaving you. Well, thanks for tuning in to the Scientific Adventures of Beardman. Go out and listen for things coming towards you and going away, and perhaps you'll hear that Doppler effect. Feel free to move towards and away your computer really fast and see what this sounds like. Anyways, that was probably silly. Anyways, I will see you guys next time. Have a good day.